Well, good morning, physics students. Let's just keep taking a look at some of these properties of waves and see if they pertain to light waves. So we kind of started down this path a little bit in physics 142 by just looking at general properties of waves. And so that would be, the reflection of waves, the refraction of waves, the interference of waves, the diffraction of waves, the possible polarization of waves, and the dispersion of waves. And so those are just general wave properties. And so we'll start just, start looking at those one by one and just kind of see what kind of trouble we kind of get into here in chapter 24 here. And so, this picture here, is out of your textbook, but this is something that, we'd be able to do in the laboratory. Quite easily. Just get a red laser and, put it through a diverging lens to kind of spread out the laser light. And then just get some object that has sharp edges on it. And, around those edges, what you start seeing are these light and dark bands here, right? So here we're looking, looks like maybe a pair of scissors or something like that. But that banding around the edges are really places of destructive interference, the dark bands, and then the light bands are bands of constructive interference. And so what we've got here are waves hitting some sort of sharp edge and then banding around the edge. And so, there's this story, whether it's apocryphal or not, that Poisson, that you may run into his name in some math classes. When this debate was taking place in the 1800s of whether light is a wave or a particle, he said, well, it's ridiculous that it's a wave. He says, what you can do is get a quarter up, have the light hit the quarter, it'll bend around the edges, and in the middle of the quarter, then you're going to get regions of constructive interference, and you'll get a light spot. And it sounded like that students hated him so much that they actually went to the laboratory and tried such a demonstration. And sure enough, what he was saying was kind of stupid, ends up turning out to be exactly the case. And so this spot here in the middle has been named the Poisson spot. And so what you just do is just get a metal disc, shine an intense beam of light on it. And when the light hits the edges of the quarter, so if you have, say you have a quarter here and we're looking on it kind of edge on, and when the light waves come in, some of them get blocked by the quarter, right? And so, the quarter, they might get reflected off or something like that. But some of the waves hit the edges and they bend around it. And that's the diffraction of light that, when you hit some sort of boundary and you are a wave, so as the waves kind of maybe come in here, and we hit a boundary, right? They start curving here. Whereas they might have been parallel wave fronts before, and now, they kind of have this more concentric view. And so, this right here is the diffraction of light. Something that Poisson didn't really think was going to take place. And so as the waves bend around the corner, downstream here, when these waves are in the same place at the same time, you might have a spot of constructive interference, which would be then a bright spot to your eye. Right in the middle of what you would expect to be the shadow region behind the coin. And, that's exactly what we do see here. So, so this is called the Poisson spot. And, you can see in this other picture here, I've taken pictures like this in our laboratory as well. This looks like it's got a nice blue light. Typically, I just use red laser light, but here it looks like a razor blade. And you get these just beautiful regions of constructive and destructive interference because the waves hit the sharp edges and they can bend, and then you've got multiple waves in the same space at the same time. And so that's one way of thinking about doing this. And usually you can kind of get this banding of the dark and light regions here, like we see here, where you've got a dark band and a dark band, and then there's a region of light band inside there. A lot of times, if you just can get your fingers and you get them close enough, and you get something on the back side of them that's bright, like a lamp or a light, or maybe even a computer screen. And as you get your fingers close enough, all of a sudden you'll start seeing this banding, and it almost looks like fingerprints starts kind of showing up in the air. And and that would be very close to what you see here in the region around this metal disc here in the Poisson spot. You start seeing those regions form of the constructive and the destructive interference. So it's actually pretty easy to demonstrate that light does hit edges and then bend around them a little bit. Sound waves do it even more, right? We can hear around corners. That's not really much of a problem. So, when sound waves hit a door opening, they bend around the corners. Now, light waves, the amount of bending is very small. So, technically, I think we can see around a corner, but you're just talking about, fractions of a millimeter or something like that. So, it's not of any practical use or anything like that here really at all. So, how is it that people, use this idea? And probably in terms of, the scientists and being in the laboratory, the most useful tool that comes out of this is the diffraction grating. Prisms act, exactly the same way. But the diffraction grating, will be, some sort of material that has like little openings in it that are, what you really want them to do is be uniform in their distance between them. And, usually if you kind of blow up a diffraction grating, what you've got is, like a little opening, little opening, little openings like so. Right? Almost like teeth of a comb or something like that. And, if you have like green light coming in, right? So here are the wave tops coming in. And what happens is they hit these openings, right? And then you start getting diffraction here. And you get diffraction around that one. You get diffraction here and you get diffraction there. And so you get all sorts of little regions in here where the waves are overlapping. And then you're going to set up some sort of interference pattern as long as you're using one wavelength of light, just like the double slit experiment, and the light is coherent. That is, it's not changing its phase randomly, like what it does in light bulbs and things like that. And so, if you were to, kind of blow this picture up a little bit, and, if you have all these multiple openings here, and you've got some sort of screen back here, what you end up finding, say if we have like red light coming in, is that, you're going to end up with, some sort of bright spot, say right here. And so here's the path that, comes from that opening for the light to get there. And then here's the path that this ray has got to travel to really kind of get there. And, you kind of figure, well, one path, the bottom path, is obviously longer than the top path. And so there's a path difference here, right? So here's path 1, there's a certain distance there, here's path 2. And so you start thinking, well, if they're making a bright spot, then if I were to drop this down right here, this little piece right here is the path difference. That is, it's the long piece minus the short piece. That's how long that is right there. And that has to somehow be related to the size of the waves, because you're getting the waves to overlap here in such a way that they are in phase to create a bright spot. And so that little distance right there is holding like one whole wave here, right? And so it's just like the double slit experiment. It's really sort of no difference. And then, you've got this angle right here that we saw in the double slit experiment that is very, very difficult to actually measure. But when you take a look at the geometry, that angle really can be, if we start looking at different triangles here. Yeah, let me see that. I guess we can probably do that this way. Right from the center out to here, this would be the same angle right here. So here's a right triangle, and actually in this triangle right here, you've got this piece right here, we've got that piece right there, we got that piece right there. And this is really from opening to opening the diffraction grating. It's still what we call D. So your textbook just wants to call that spacing always a D. So and that's okay. So there's a little triangle, but there's a bigger version that is a similar triangle that I've got outlined here. And so it's really the same angle. But with the diffraction grating, the wonderful thing about it is that we really can measure that angle. We can measure that angle with precision, all the way down to probably thousandth of a degree or something like that. And with exactly the same sort of mathematics that we saw last time, that if I were to blow this up even more and look at that triangle right there, from here to there is the distance between the slits. And so this side over here is D times the sine of the angle. But that equals really the path difference, right? And so we run into this mathematics that the path difference, to get a bright spot, has to be on the order of like one whole waves or two whole waves. So if you're fitting a wave in here, you can fit two, but but maybe that holds one whole wave, and then it just repeats that all the way down to where it hits the screen, and then the top, or delta 2, that top path has one less wave in it, but that path difference is D times the sine of theta equals m times lambda, and this is for the bright fringes, or the bright spots. These are spots of constructive interference. And here m can be 0, that is no path difference, one whole wave, two whole waves, three whole waves, four whole waves, and so forth. And so you get this pattern, but because you've got more openings than just like the double slit experiment, there's advantages here. And one of the advantages is that the pattern here is more intense because there's more light getting through, there's more openings, and then it's sharper. Okay, so you have the sharpening of the pattern that shows up on the wall, and it is brighter, and so that makes life much better. And if you can measure the angle, in this case, there is really no reason to approximate any sort of angle, with the sine and angle becoming, in the last lecture, the tangent of the angle. And the tangent of the angle is just about the ratio of one side to the other side of the triangle, the opposite divided by the adjacent. And here, we don't need to worry about that because we have built devices that can measure that angle very nicely. And that's what a spectrometer happens to be. And so, in a spectrometer, if you really take a look at what's going on here in this equation, Notice a couple things here, right? If you're building the diffraction grating, you have full control over D. But what you can do here is let light come in to the openings, and the light can be of different wavelengths, okay? And so you let light come in of different wavelengths. So different wavelengths will have different angles, okay? And so usually, like in the laboratory, what you might do is get a light source. And so, here's maybe a light source. And I'm looking down, and it's just maybe like, it's not really a light bulb. But what it would really be would be a tube that's got metal on the two ends of it, and it's got a gas inside of it. And those two little metal pieces actually go in, and we put about 5,000 volts across it. And what that does is makes the gas light up, right? So then light is coming off this gas. And so you can do this with hydrogen or helium. And usually that's what I would, start with is probably like hydrogen. And so this light comes off of that light source, and it's got a color to your eye. And something like hydrogen would be kind of purplish pink. And so there's lots of, it's very dominant in the reds and so forth. And you catch that light. That is, the light goes everywhere. But you have a little tube right here. Okay. And that little tube will actually have maybe some optics. That is maybe a lens on here, so that the light that comes through, we can sharpen it up. We can get it to be very, very narrow in its banding and so forth. And here's where you really spend your money here. You build something that it looks just like what I just did right here, right? This is a nice perfect circle. And in that nice perfect circle, you actually etch it from 0 to 360 degrees, but you have little verniers on there so that 1 degree can be broken apart very, very nicely. And so the light comes down the tube and then hits right here, your grating. So here's the diffraction grating. And say if this light has multiple wavelengths in it, they get sent to different angles, okay? And so what that means, and we'll take a look at this here, is that if there is, like red in here, maybe the red beam comes like that. And if there's green in here, maybe the green comes in here like this. Oops, let me think about that. How about this? I'm looking at that equation, and the long wavelength is going to be down here. So the red light might do that. Maybe the green does this. And then maybe there's some purple light in there, and it does something like that. And what we do is we build a tube over here, and we look through this tube. And the tube can move along this protractor. And so you move it until you find the purple band, and then you can measure this angle right here to the purple band. And then you can let this thing slide over, and then you find the angle to the green band, and then you let it slide over, and then you can find the angle to the red band. And so you can find these angles here with precision. And this is how probably most of the time the professionals will be measuring wavelengths of light using this thing called a spectrometer. And so, you do have to have a very fine diffraction grating. And these tubes have a little bit of optics, and there's a couple little lenses usually in there just to get things sharp for, one person's eye. It's going to be different from another person's eye. But what you're really spending most of your money on is having a very finely detailed, really a protractor there, that this other tube can glide along that protractor and you can, line up, right on the protractor to start with, and, say, okay, here's angle 0, and then you're going to measure all your angles from that. And so this right here just works very, very nicely in the laboratory if you've got the device that will allow you to really kind of, use what the laws of physics here, says is going to happen. And so, what we find out is something like hydrogen gas would have a red line. And so, it's going to have this red line that's, very, very famous. And so there's this red line that comes out of hydrogen, and it's about 656 nanometers. And then, there's some sort of kind of bluish green light that kind of comes out of hydrogen. And excuse me. And then there are, like 2 purples that are pretty close to each other. And, as I recall, maybe this kind of bluish green light is maybe something like 486 nanometers. And maybe one of these is like 434 nanometers. And I can't remember this last one. This last one is 410 or 404, something like that. But those 4 colors are in the visible spectrum. I think there's other light waves that are coming through, but our eye doesn't see them. But these 4 colors with those wavelengths would be something for hydrogen gas. And so essentially that is the fingerprint of hydrogen, because only the hydrogen atom has exactly those colors coming from it. So when the astronomers, say something like the sun has hydrogen gas in it, well, they're not just guessing, but there's a measurement. We look at the light that comes from the sun, and you start seeing these bands in it, and oh, okay, I see the telltale sign of hydrogen gas there. And then you would do the same thing, right? Then you would try something like helium, and so you get some helium gas in a little tube and do the same type of thing and see what colors come out of helium. And once again, when you look at the sun, you start seeing a lot of helium, coming from in natural sunlight. And so, a lot of stars out there can be analyzed according to their spectra. And so that's the light that comes from them. And so we can identify, what chemicals are there. So, once the physicists have made that a spectrometer, and we've made these measurements on, some of the different gases, right? Then you just give it to the chemists and let them, finish up the rest, right? Because there's probably better things to be doing, once you kind of get this thing going. But, all gases then are going to have some sort of known spectra. And so this is going to be something that's going to be very important for identifying, the type of gas. So you're stuck here on Earth if you're the astronomer. And so, one of the few clues that you've got is this light that comes to you. And in fact, you will sort of see here maybe in about a month or so that, if you look right at the center of the sun, this is actually the numbers you would get. But if you actually look at the edges of the sun, you get numbers that are just a little tiny bit off from this, just a little tiny bit, because the sun actually is rotating. So one limb of the sun is rotating towards you, and one limb of the sun is rotating away from you, and that actually affects the wavelengths of light a little bit. So I actually have a telescope at the college that can be fine-tuned to those differences when you're looking at sunlight, and it can be tuned so finely that you really can't look at both sides of the sun at one time, because one side will be in focus, but the other side will be out of focus, because whether the sunlight is coming or going, the wavelengths gets changed a little bit, and that's called a red shift or a blue shift. And so these wavelengths get changed a little tiny bit, and that then will tell you how fast the sun actually is rotating. This is actually how the police officer knows how fast you're driving and that sort of thing as well. So looking at those shifts. And so, the idea of using, two openings here to in the Young's double slit experiment really kind of opens up the idea that light is just behaving like a wave. It's acting just like a wave. And so then when you have multiple openings, you have this idea of a diffraction gradient. It really leads to something much better in terms of going to the laboratory and making these measurements that help us identify different materials. And in fact, it'll tell us whether stars or galaxies are moving towards us or away from us, or whether the sun is rotating towards us and from us as well. So there's actually a lot of very interesting physics that's kind of wrapped up here. And of course, this here is for constructive interference. This is for bright spots here. Okay, oops. And so let's take a look-see here. What else we've got? Probably we should look at the idea of single slit diffraction. And this is kind of surprising to a lot of people, that if you have just a single opening, and you put a screen kind of downstream, what you end up getting is a bright spot, and then no light, and then a bright spot, and then no light, and then a bright spot on this side, where maybe this here is called the central maximum. And this kind of almost seems odd that light would go through a single opening and still downstream have a interference pattern here. And you kind of figure, what the heck, is going on with something like that? And what you have to really do here is recall Huygens' principle. And Huygens' principle tells us that every point on a wave is like a source of tiny wavelets that move out from the wave and we can approximate those wave fronts with rays that go at right angles or tangent to them. So, when the wave comes in, so maybe you've got these red waves that are coming in here. And, if you get a bright spot someplace, or get a dark spot someplace, something interesting then is happening here with the waves. So let me get let's get that color. So I'm going to go right from the edge of the opening here, and your textbook still wants to call this D. A lot of times textbooks will call that A for the aperture opening. But I'm going to go right here to this dark spot, and I'm going to go right to that edge right there. I'm going to go right to the middle right here. Okay, and so for that dark spot, once again, I've got two different paths. And so one path is longer than the other path. And it's not a big deal, but it's enough, right? There's the path difference right there. And that path difference has got to be then like a half of a wavelength off to create a spot here of destructive interference. Because what I really have there is no light, right? There's no amplitude there, whatsoever. And so this path difference right here, that little piece right here, has to be something like a half of a wavelength. And so if I get then a light wave from down here at the other end, so what I wanted to do is really kind of pick this point right here to be the midpoint to the aperture. So from here to there is d over 2. And so from here to there is also d over 2. And so you get a ray coming from down here, a third path that's hitting that spot. This is going to have to be a dark spot as well, because that path difference is this much right here, and that's going to have to be a half of a wave as well. And so, what you've got here is something that's behaving a little bit like multiple slits, because really when this wave hits this opening, right? So if you kind of think about this in terms of Huygens principle, that you've got this opening here, and this wave comes in and hits that opening, and it starts bending, right? You start diffracting. And so this right here, and 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 this right here, these are all like spots of multiple waves, right? You can think of each spot here as a source of tiny wavelets. And then you've got these rays that have got to cut across these, at right angles and so forth. And so it's like you've got these multiple rays that are coming out of just one wave here. But because it bends at that corner, or at this opening, this aperture, you end up with something that starts behaving a lot like a double slit, or more like a diffraction gradient here. But what we have here is the path difference in this case, from the middle of the aperture to the top of the aperture. So I was really just looking at my aperture here. I was looking at a spot here where that's D, and this was like D over 2. And so what you get is that path difference when you start drawing your triangle up, starts looking something like this, where that's D over 2. And here's that angle that's always kind of an issue. And here is the path difference. And that has to be something like half of a wavelength for us to get a dark spot there. And so, what you've got then is some physics that says something like, D over 2 times the sine of that angle. That's just the hypotenuse, times this angle, which then calculates really this path difference, right? And so that side right there is just D sine over 2. And that has to be equal to something like a half of a wave for now a dark spot. And so it looks like, those cancel out. And so when you have a single slit here, something like D sine of theta gives you something like the wavelength. And, this happens multiple times. So you can be off by one whole wave or two whole waves or something like that. And this is for the minimums or the dark bands now. This is for the dark fringes, or sometimes they're called the minimums or the minima. And that right there then is the condition, the mathematical condition, to get spots of destructive interference in a single slit here. So these are spots for destructive interference. And so, a lot of times, in the laboratory, I'll just go to some girl that's got long hair and I'll yank a hair out of her head. And, we can kind of tape this up, that piece of hair, and let the laser hit it. And what happens is the laser gets, some of it reflects off the light, but some of it hits, the hair. So if this is the hair, let's get a color that actually shows up a little better. It's not having terrible hair day today, but okay. So if this is the hair, and so every so often, maybe I get somebody who's got pink hair or something like that. The light wave hits and gets reflected, but some of it hits and bends over the top, and some hits and bends under the bottom. And so then there's a region down back behind here, just like the Poisson spot, regions of constructive and destructive interference, depending on where you're looking, right? And so if you're right in the middle, then the wave off the top and the wave on the bottom have traveled the same distance. And that's a bright spot. That's the central maximum. But if you kind of go off to the sides, you get bright and then dark, then bright, then dark, then bright and dark spots. And so actually what you can do is just measure the light and dark spots with the ruler which is the distance between them. And then just use a little bit of geometry, and you can actually work backwards to, figure out how, actually how, what the diameter of that hair is, because essentially that is the aperture here. Because you're doing is allowing waves to come over the top and the bottom of it, and so you're really spacing waves out, in a way to get some sort of diffraction pattern here. And this is just kind of just another demonstration that light is behaving like a wave. And for the most part, I think that this hasn't been, maybe as useful to the scientists, maybe until really, the last 30, 40 years or something like that, in terms of creating a technology out of this. But even though CDs are kind of on their way out, what it really has is just a whole number of fine grooves in there, and a laser hits that, and the diffraction patterns that are created from there is exactly how this thing is actually doing some reading of the information that happens to be sitting there. So, just kind of very interesting, but just another place where light is behaving just like a wave, and we can work out, exactly what's going on here with some sort of precision. And what I should probably leave you with is, if M, equals 1 or 2 or 3, these are for the dark bands, the dark fringes. And if you want to get the light fringes, then you're off by half that distance, and you can start using like halves in here as well. And these are for the light bands. Okay, so that's just the mathematical conditions of what takes place here. So, what I usually end up doing is remembering that d times the sine of that angle equals m times lambda gives you bright fringes in the double slit experiment. That same condition, d sine theta equals m lambda, also gives you bright spots in the diffraction gradient. And then when you get to the single opening, then d sine theta starts giving you the dark spots. And so it's the single slit that really has the condition that's different from the other two places that we've looked at here so far. But kind of interesting that light will still create some sort of pattern here just by going through a single opening here. But Huygens principle does a nice job of helping us out with different aspects of that here to understand what's taking place. Okay, what do we got next here? The dispersion of light. Okay, so you've all seen rainbows, and so take a look-see here of what's kind of taking place here. So we have white light coming in. Is that right? So there's white light coming in, and then you get all these different colors coming out here, off the other side. And what's really taking place here. But this is called the dispersion of light, and this is a problem for telescopes that use pieces of glass. Those are called refractors. So light hits the lens, refracts, and we're using Snell's law and to refract the light to go to a different focal point and create images, different magnifications and so forth. But the problem is the light that comes in from like stars or planets or the moon or wherever it's coming from, right? If it's coming from the planet or the moon, right? These are reflected light that's coming from the sun, but there is some absorption on these planets, with their atmosphere, or the moon off the surface, where only maybe certain colors come to us. But what hits your telescope is more than one color of light. And when it goes through the piece of glass, it breaks into like a rainbow. And so this actually makes telescopes have something called chromatic aberrations. And if you use two pieces of glass, and typically the one out in front is called the objective, and then you have one near your eye called the eyepiece, you will typically see funny colors on very, very bright objects. We can make that go away by adding a third piece of glass. We can get those different colors and put them back together. And that's called an apochromatic telescope. But then to make perfect glass and to have it perfectly made with no bubbles inside or any sort of artifacts inside and then perfectly polished is expensive. And you add a third one, well, that just adds to the cost of your telescope. But if I was going to buy a refractor, I would make sure that it's apochromatic. Otherwise, you look at something bright like the moon, and around the edges, what you'll see is like lime green colors. Sometimes I've seen purple colors, and you go, okay, there's these artificial light that's showing up here. And you really kind of don't want that, right? You really want more of a natural view here. But the thing here that's important for us is what's taking place here, okay? Why is light behaving like this? That is, why do the reds go to one place and why do the violets go to some other place? After all, what's really taking place here is just really refraction, right? And so we have a law of refraction, and that law of refraction looks something like this. That's Snell's law. Okay, and so all the light is coming in essentially in a beam, and so it all has the same incident angle, right? So that's really no different. But what's different is that the different colors have different transmitted angles, right? And it's slight, but it's there, right? The reds kind of go to one angle, and the violets go to somewhere else, and the greens are kind of in the middle. So for you to be getting different angles, what is happening is that that piece of glass, its index of refraction is not really just a single number. It is dependent upon the wavelength of light that's hitting it. And so you go, that kind of seems odd, but not really, right? Somebody kind of give you a conceptual way to think about that. But that index of the transmitted material is c divided by the velocity of the wave going through that material, right? So that's what an index of refraction happens to be. And so remember, I probably mumbled something like this at one time or other, in one of these lectures. I lose track. You got a proton, you got an electron. Right there, we have hydrogen gas, okay? And this electron, we conceptualize this as kind of going around in some sort of orbital or something like that. Now, you can change the speed of that electron by having it absorb energy. And how does the electron absorb energy? Well, it absorbs a photon of light, one particle of light, okay? So a light beam comes in, hits that electron. The electron grabs that photon and it's gone. It's gone from the universe. But the electron has picked up this energy, and so it's going to go faster, which means it spirals out to a bigger orbital. So maybe this is like the first orbital, and that's called n equals 1. And so maybe it speeds up because it absorbed some sort of energy. That energy we call it a photon. And now the electron is in this other orbital. Okay, and so then it spins around a few times. This is not its lowest energy state. And so then it will release that photon, and then it'll slow it, and then that's essentially slows it down. And so then it can go into a tighter circle, right? If you're in a little tight circle, you can only have a certain speed. If you speed up, then you just kind of spiral out. That works the same way in your car, right? Trying to go too fast in a tight curve, you can feel, that inertial path, kind of sort of taking over here. Now, the energy from the first orbital to the second orbital is small, okay? But the electron can absorb more energy and then maybe go out to this third orbital, okay? So that's a bigger jump from the first orbital. So it can go from the first all the way out to the third. It can go from the first, you can knock it all the way out of the atom. That's hydrogen, you need 13.6 electron volt photon to do that, and so forth. So these numbers are well known. But if you knock it further out to these further orbitals, that means more energy. The light that has more energy are the blues and purples. The light that has the least amount of energy are the long waves. Those are the reds. And so, this right here might be like a reddish photon, right? And then this other one is more energy than a reddish photon to knock it out there. So that it takes longer to get out there. Then it spins around a few times and then it drops back eventually back down to the ground state. But when you knock it to a further orbital, that's a bigger trip, right? The electrons don't just instantaneously go from here to there, right? They have to kind of move that distance, spin around a few times, kind of come back. And so there's this slowing down of the wave, right? The wave keeps hitting these electrons, gets absorbed, gets re-emitted. But if you knock the electron out to a bigger orbit, that absorption and then re-emission of a new photon takes longer, a small amount of time, but longer, right? So different colors essentially have different velocities in the material depending on where they really knock that electron, right? So it's not really that surprising that something like violet, which has the most energy of the light that we see, knocks the electron out to a further orbital. That takes longer. If it takes longer, then the velocity of that material is slower, which means that the index is slightly different from color to color. And so, at least conceptually, you can kind of think about it like that. And I think in your textbook, you've got something that looks like this here. And so it shows you that, right? If you have something like a piece of glass, right? So right here, like glass, the index of refraction for something like violet light is like right up here, and it's very close to, well, so this is like, so this is something like 1.5, like 2 or something like that. And then something like red light is something like 1.50, right? Something very, very small. It's down in the decimal places, but it's enough that when you go to something like Snell's law, that small difference in the index gives you a slightly different angle. And so then the reds come out from a refractive material, a transparent material, and a slightly different angle than do the violet light. And so then we have the rainbow being created. And so this is exactly what happens with the rainbows with white light going through some sort of raindrop or something like that, some water drop that's hovering in the atmosphere. And but there's slightly different indices for the different colors. And so violet has a slightly bigger index, so it has a different angle than the red light does. So, so that's kind of interesting. And so, anybody that takes this course should have an understanding of, how rainbows are created and so forth. And so, well, there you got it. Okay, what's next here? The polarization of light. When we probably started this idea of light being a wave, and it's really much more complicated than what we show here. But okay, here's a wave. And if this is a wave and this is a light wave, what we really have is this other aspect of the wave that kind of goes kind of in and out of the page. That's the magnetic field vector. And this is the electric field vector. Okay. And so what you've got is an electric field in the electromagnetic wave that is always at right angles to the magnetic field. Okay, so this is in an electromagnetic wave. At least the waves that we will look at. So that may not always be the case, but the ones that we will look at, always be kind of the nice, simplest wave to kind of deal with. And when I draw it this way, notice that the electric field, which is really the black serpentine line, is staying on the piece of paper. And really the magnetic field is kind of going out of the paper and then goes into the paper and out of the paper and into the paper. And so what we would say is that that wave is really already polarized. And what that really means is that the electric field stays really in a plane. And maybe this would be the XY plane or something like that. Right? So the electric field here is essentially just kind of doing something like that. Right? And the magnetic field then is going in and out of the paper. But this what we would say is plain polarized light. The electric field stays really just on the piece of paper. Now, when you have a light bulb out in front of you, there's electric fields that are coming towards you that are like this, but there's also electric fields that are coming to you like this, and any sort of angle you can imagine. So light bulbs are creating waves that the electric field has an orientation that is all over the circle, right? You can have electric fields like this, like this, like this, like this, like this, like this. And so all the way around from 0 to 360, the electric fields can be coming towards you. And that's what we call unpolarized light. That's natural light. Light that comes from the sun is unpolarized light. The electric field has any kind of orientation that you can imagine. Light that comes off of a light bulb will be unpolarized light. Okay, so light that we find in nature will have the electric fields in all sorts of orientations and so forth here. And I think the story goes that I think somebody probably working for I think Kodak came up with something pretty clever here. And what you get a transparent material here. So a piece of glass. And you're going to put essentially a coating on the glass. Okay, so that's just a chemical. So you just get the piece of glass, dip it into the liquid material, or you spray it on. And as that chemical is drying, you subject the piece of glass to an electric field. And because the chemical that you put on it is a special chemical, and it has long hydrocarbon chains. And so when you hit these molecules with this electric field, their positive and negatives will then rotate like little compasses will with a magnetic field, and they will line up with the electric field. And so you can get the majority of the little electrocarbon, or they're long hydrocarbon chains, and they line up in here. All right, so you have all these little chains in here. And so the molecules get aligned by this this electric field that you put on this piece of glass before the stuff is totally dry. And so when it dries, the chemical, which has long hydrocarbon chains, it dries with those molecules aligned up a certain way. And because they're long, that's important. So when light actually hits that piece of glass, it has this chemical that's been dried on it. And so when you look at the piece of glass, to your eye, it would look like tinted glass. It would look darker to you. Okay, it's just like the tinted glass on a car or something like that. But when the light hits this piece of glass, those hydrocarbon chains, since they're not just randomly organized, they're lined up almost like bars on a jail cell. They let light through that has one electric field orientation. When I say one, the electric field really could have any orientation that it wants. But, say the orientation is like this. There is an X component and then there's a Y component. An X component and a Y component. X's and Y's to any vector, right? If it's like this, then it has an X component and it has a Y component. So something horizontal and something vertical. So what happens is those hydrocarbon chains, since they're lined up a certain way, it really allows one of the components to get through and the other component doesn't get through. And you see here how the hydrocarbon chains are kind of up and down, kind of like in the Y direction. If I put like a piece of graph paper on this, we would probably call that direction the Y direction. That would absorb actually the Y components of the light. And so if the electric field has an orientation like this, there's an X component and there's a Y component. But this Y component of the electric field, when it hits these carbon chains, the charged particles on the carbon chains feel this electric field and it's changing, right? And so the charged particles on the hydrocarbon chains are getting pushed up and down, just really like what happens on an antenna, like on your car. And so your antenna grabs that wave and the same thing happens here. So really here, what we would say is that the transmission axis here is this way in the X direction. The waves that are going sideways, or the X component of the electric field, can make it through this glass because on the hydrocarbon chain, right, the charged particles have no room to kind of move back and forth. But up and down they can, right? So they can act like an antenna up and down. And so those are the waves that they're going to absorb. And so that's the transmission axis. The absorption axis, I don't know how that letter came out of my hand. The absorption axis is along the hydrocarbon chains. And so what ends up happening is that the light hits this glass and it has what we call a certain amount of light. And we've actually looked at this word before when it came to sound waves. That was, we used the letter I, intensity, right? So there's a certain intensity of light here, but this piece of glass, because it has tinting on it, but the tinting is very specialized tinting, it absorbs all of the Y components of the electric fields. So the only electric field that is left standing on the backside of the glass are the X components. And if you figure unpolarized light, which has any sort of orientation that you can imagine, what you're doing is taking out one of the components. So what's on the backside of the piece of glass is 50% of your light, because one of your components just disappeared. It doesn't matter, because you can get that piece of glass and you can just turn it, right? And now the transmission axis and the absorption axis are just different from what you had before. But whatever is on the back side of the glass is always going to be 50% of the incoming light. So you lose half of your light, which is why, tint works, right? Because what you're doing is knocking down some glare or something like that. But what's more important here maybe is that on the back side of the polarizer, all of the electric fields are lined up. They all have one orientation, much like the picture we have up here, where the electric fields are all just along the y-axis. They're going up and down the y-axis, and they're kind of serpentining their way along the y-axis, where the magnetic fields are kind of going, in and out, like along the z-axis or something like that. And so a polarizer, what it does is it aligns the electric fields because it selectively absorbs one of the components. Okay. And so, if you then get a piece of glass, but a lot of times in the laboratory, they're circular. And they're circular because somehow this angle is going to be important to it. So it's easy to tell angles on a circle. So if you have something that is, a polarizing material. And here is the transmission axis. Okay, and so you have these light waves that are coming in, right? And so out here, you have light that's coming in, hits this essentially a little piece of glass made of, you know, the special tint material on here. And I0 is the initial intensity of the light, okay? In that, if this is unpolarized light, then it has its electric fields in every orientation that you can imagine. But this transmission axis is only going to allow Y components through. And so the electric field that is in here are all like this. Those are the electric fields that survive. And so usually, so that you don't think about having to draw you know, every orientation possible, unpolarized light, the electric fields have a Y component, and you know, maybe they got this X component, but this gets absorbed. Right, so what's downstream is just then the electric field that lines up with the transmission axis, and the intensity here is half of what you started with because the X component's gone. And so, you know, if one of the components disappears, then, you know, you're left with the other half. And so this is what always happens, that the intensity, you know, on the backside of a polarizer is half of what you started with, but that light now is all lined up here, okay? Now, something quite interesting happens if, right, you have a second polarizer. So if you have a second polarizer here, and let's say that its transmission axis is like that, then you figure, oh, okay, is any of the light going to make it through? And the answer in this case is yes, some will. And that's because you can come in here and, right, any vector has got components. And so you can put, you know, put them head to tail. So put two little components so that this component right here lines up with that transmission axis. And then that's what's going to sneak through here, are just those components. And so that's what's left standing. And so I'm going to call this I2, I'm going to call that I1, and then I'll call this over here I0. I0 is before it hits a polarizer. I1 is the intensity after the first polarizer. I2 is what happens after the second polarizer. And you figure, wow, okay, let me think about this. Now, the first polarizer is kind of along the y-axis. Now, what if I put the second polarizer and this transmission axis was along the x-axis? So they're at right angles. Then you would think, well, this is going to pick, you know, allow the y's to go through only. And so when you hit the second polarizer, there is no x component to transmit through. So it all gets absorbed. And so then there'll be no light. If the two polarizers are at 90 degrees, there is no light at all on the backside of the second polarizer. But now if you rotate that piece of glass so that the transmission axis line up, then the light comes in, hits that first polarizer, and all the electric fields in here are all along the y-axis. And then you hit the second polarizer, and oh, that's the transmission axis, and they all go through, right? So here you have I0, here you have I0 cut in half, and then over here you would have I0 cut in half because it all gets through, right? So if the two polarizers have no angle between them, all the light gets through. If they're at right angles, no light gets through. right? So you start thinking about, well, what function does that? Where the angle is 90 and I get nothing. And if the angle is 0 between the two polarizers, it's the same. And so that kind of starts sounding like a cosine, right? Cosine of 0 is 1. That means really kind of no change in terms of intensity. But cosine of 90 is 0, right? And so if you have the second polarizer, this thing kind of comes up, and it's called the law of Malouche, or students call it the law of malice, because it's physics we have to learn. And what this really tells us is, the angle between the polarizers is what's important. So here, in this case, right here is the first polarizer, and then I've got the second polarizer. It's that angle right there that's important. So here's the first polarizer. Here's the second polarizer. And there's the angle between them. And the law of Malouche tells us that the intensity 2 is the same as intensity 1 times the cosine of the angle between the two, right? So if the angle is 0, they line up. Cosine of 0 is 1, intensity 1 and intensity 2 are the same. If they're at 90 degrees from each other, then the cosine of 90 is 0. Then intensity 2 is 0. There would be no light getting through that second polarizer. Now, cosines go not only from 0 to 1, but really from -1 to +1. And when it comes to intensity of light, intensity is like gallons or of like water or something like that. There really are no negatives here. And so we had to have no negatives here at all. So the way that we end up getting rid of negatives is that, it's going to be actually the cosine squared. And so, that always turns the number into something positive. And I'll show you here in a moment, kind of how this is working. It's kind of interesting. If you really understand what's taking place here, you can actually, in class, I would bring some polarizing sheets and, just let light go through them. And, when you've got these two pieces of glass, and then you just start moving one, just start rotating it. And, all of your faces that I'm looking through the piece of glass will disappear at some place, which usually is good. But then eventually, all the light kind of gets through from the first polarizer, and then you can just sort of blacken everything out. And it's very, very interesting, really kind of how this kind of works here. But you can find two polarizers and find the spot, because, on a piece of glass, there's no arrows drawn where the transmission axis happens to be. And so you just kind of do this by trial and error. And once you, find where you can blacken all the light, that is, absorb all the light, you can put a third polarizer between them. And even though the first two are crossed from each other, you put a third one in here, and then light will survive through then, all the polarizers, which is kind of interesting how that might actually work. So you might want to kind of think about that here a little bit. But let me kind of show you how this works. And this might be a good time to have your, calculator here ready to go. Okay, the axes of two polarizers make a 50-degree angle to one another. Unpolarized light strikes them. What fraction of light intensity is transmitted? Okay, so this is telling me something like this is happening here. Right? The first polarizer is like this. It doesn't matter how you orientate the first one. It just polarizes the light, because you really don't know in real life. And then your second polarizer is 50 degrees from the first one. Okay, and so you just kind of think about this as being like a little disc, a little glass disc. Here's the little glass disc. Okay, and here we have some intensity of light, and we don't even care what that happens to be. Right? After that light goes through that first polarizer, after the first polarizer, half of your components are gone, right? So one of the components is gone. Now, the question here is really, what is surviving past that second polarizer? Okay, and so that's where the law of Malouche here really sort of allows us to calculate this pretty nicely, pretty easily. It's I2 equals I1 times the cosine squared, the angle between them. Now, I1 is the same as I0 cut in half. And that angle here is 50 degrees. And I'm going to square that. And that is what survives the second polarizer relative to what we started with. So we don't even know what we started with, but we're going to end up with a fraction here, right? So I'm going to go to my calculator, hit 50, hit the cosine. It says like 0.64. I'm going to square that. Then I'm going to multiply it by 0.5, which is 1/2. And, you know, I think I end up with something like this. Okay, so this right here is like 0.5, and this on my calculator, 50 cosine, and I square it. This is like, you know, 0.413 or something like that, and 1/2 is something like 0.5. And when I multiply them together, I get this 0.21. And so in other words, 21% of the incoming light, I0 is the incoming light, survives two polarizers that are 50 degrees from each other. And if I make that angle 90 degrees, we would end up with 0, right? That is, I2 would equal 0 right? The whole thing would just sort of die out here very, very fast. But something to kind of catch on to is this right here. This is important, right? That unpolarized light happened to strike them, right? That's going to be kind of important here. So that's just natural light from a light bulb or from the sun or something like that. And so when I take a look at this example 2, it's exactly the same two polarizers. They haven't moved, but now we're going to change the light that's coming in. It says, answer the question above. If polarized light initially strikes the two polarizers, the incoming light is 25 degrees from each polarizer. Okay, so in other words, there's really a third polarizer here, and it's out in front of the first one, and it polarized the light. Okay, and so you really then have light coming in, and it's already polarized. And so the answer will be different than, you know, what we have here. Here we had 21% that survived. Now it'll be a different amount. Okay, so let's think about this here. Here's the first polarizer. Let's just have it like that. So there's the first one. And here's the second one. And they are 50 degrees apart. Now the light's coming in and it says it's 25 degrees from each polarizer. Well, how can that be? How can the light and its electric field orientation be 25 degrees from each polarizer? It's got to be like right in here then, right? So the incoming light has got to be 25 degrees from that polarizer, and it has to be 25 degrees from that polarizer. Because I think that's what I'm kind of reading here, is that the light is 25 degrees from each polarizer. And so when I'm kind of thinking about this, right, I've got my first polarizer here, and the light's already coming in. So I've got my first disk right there. And the light's coming in, and it is 25 degrees from that. Okay. And so that's a calculation, right? I already have now light that is lined up hitting another polarizer. And so right here, you know, I've got to, you know, do something like the law of Malouche here. And so This is, I0 and this is I1, but, I'm going to have to do a calculation here. And there are 25 degrees between those two vectors. And so I'm going to go to my calculator. I'm going to hit 25, take the cosine, and I'm going to square that, and I get 0.82 or something like that. Okay, so 82% of the light is in the space behind the first polarizer. And that kind of makes some sense here because, if you can just kind of looking at vectors here, right, this light vector, it's got an X component, it's got a Y component. And the Y component lines up with that transmission axis. So the light in here is all like this. Right? So its orientation now has changed from kind of coming in skewed a little bit, hits that polarizer, and now it's all like this, but it's a lesser amount, right? Because some of the components have, so this is the electric field here. But what we have in this region of space here is about 82% of what we started with. Then you hit the second polarizer. And the second polarizer is over, oriented like that. And what you've got is light that's coming in like this, right? So how far apart are those two? Well, it seems like these two vectors here then are 50 degrees apart, right? Because here's the light that survives the first, or the component that survives the first polarizer. And so now you've got a second polarizer and it's got a different orientation. So, I2 here is going to be I1 times the cosine squared of the angle between them. And, I2 here equals I1, but I1 is the same as 82% of what we started with. And what we have here is 50 degrees between those two vectors, and that's going to get squared. This is going to tell you the the overall amount of light that survives. So cosine of 50, square it times 0.82, and I think I'm getting something like about 34%. Something like that. Okay, so yeah, it's important whether the light is polarized or not here. Okay, this is all fine and interesting, but what advantages do polarized lights have? Well, polarized light happens in nature, and so when light actually reflects off of a surface, one of the components is more strongly reflected than the other one. And so if you have something like water, so if you're in a boat, or maybe you're a lifeguard, you're looking over a pool of water, and the light hits the water and then comes up to your eye. The light that comes up to your eye off the surface is got an orientation that is different than natural. When you look up towards, just towards the sun, that light has got electric fields that have all orientations. But the reflected light is more strongly reflected in either the X or Y component, depending on angles and things like that. And so if you wear glasses that have got some sort of polarized tint on them, then what it's going to do is knock out the light that is coming off of the surface from the water better than if you didn't have polarized material there. And so the optical engineer who designs the polarized lenses does not know exactly the orientation of the electric fields coming off of this particular pool, and so they just kind of do an average. But if you have polarized lenses, you can just kind of start turning your head, and eventually you can almost get rid of all glare that is coming off of some sort of surface like that, which then is good for your eyes, right? Get rid of that glare. It helps you see sort of into the water. So if you're trying to keep little kids safe and things like that, if you're a lifeguard, but it protects your eyes as well. And so this also is helpful if you're doing a lot of skiing, right? You have this white blanket of material, all the snow out there. The light that's reflecting off of that is more strongly reflected with one component or the other. So if you've got polarized glasses, you can knock one of those out pretty easily, and so that reduces the glare. So nature polarizes light, and so we find places where that that actually happens. And so one place that happens is in birefringent materials. Birefringent is a material that has two refractive indices. And so these have two indices of refraction. Well, how the heck does that work? Most of the time, glass is right. You get the silicon, the oxides, and different things, and they all kind of get melted together. But there are places in nature where you just don't have kind of this mishmash of molecules kind of put together. And so you could have something in nature that is kind of shaped like this. And these would be crystals. And in crystals, you've got atoms that are kind of in called a lattice site. So I'm trying to draw a crystal here. That might look something like that. Okay. And now, a light beam that hits this crystal, if it's traveling this way, right, it's got a molecule to deal with, a molecule to deal with, a molecule to deal with, and a molecule to deal with, right? So there's sort of an alignment of molecules that are kind of in its way. Now, if the light comes this way, right, it's got this molecule and that molecule to deal with, and there's not as many. So in other words, the crystal is not symmetric, right? I think maybe if you get something like a salt crystal, maybe that crystal is symmetric. And if it's symmetric, then the light's going to go just as fast this way as that way. But the light is going to go faster this way, and it's going to go slower this way, just because there's more hurdles in the way, right? There's just more absorptions and re-emissions going one way than the other way. So the light does not travel the same speed depending on which way it hits that crystal. And so this is why it has two indices of refraction, because you remember an index is c in the vacuum divided by the velocity in the material. So the velocity is important. And here you've got two different velocities depending on which way the light happens to go. So something like a crystal in nature is what we would call possibly a birefringent material. It has two indices of refraction. And so what that means is, if we had a big chunk of this stuff here, the big chunk of this crystal here, and usually in the lab, I would give you, some sort of Iceland spar or something. And out here, you just have natural unpolarized light. Okay. And so the way that we show unpolarized light is that it has an X component and it has a Y component. So the light is say it's going to hit right here. So you have a beam of light and it's got that component. It's got that component, right? an X component and a Y component. But this material, because its atoms may be, or its molecules may be more kind of densely packed in one direction than the other direction, these two components then are not refracted the same because you have two different indices of refraction. So when the light comes in, what happens is that you get a beam that is got one component, and you get a beam that's got the other component. So this is the electric field here. And well, let me just put that right exactly in the X direction. I'll put that one exactly in the Y direction. I think that'll probably a little better. So say that's the Y component, the electric field, and then this one's got the maybe the X component. And so what ends up happening is that you've got then the two components have different indices, so they have slightly different refractive angles, right? So just measuring from the normal line. And so this ray hits over here. Now maybe this ray hits down here. And then you have, some sort of refraction here too. But, this ray comes out here and this ray comes out here. But this ray here has got Y components on it. This one right here has X components on it. And that's exactly what we call polarized light. So two beams will come. And so usually I can get a crystal, on big ones, or for us are about this big, and you can just put it down on a piece of paper and, under the paper is some writing, right, on a book or something. And what hits your eyes would be two different versions of the word that's underneath the crystal, right? You see two images of it. And how do you know the light is polarized that's coming off the crystal? Well, you just get a polarizer, you just start rotating it, and you see the word kind of jump back and forth because either you're choosing this version of the word or that version of the word, because one version of the word has got Y components and the one's got X components, and you can select them. And so, we find, nature creating, polarized light too. And so, maybe the first time we really notice it is, when you make it in the Kodak lab, 100 years ago. But, since then, since we can make polarizers, it's much easier to then identify polarized light. And so this is kind of interesting here. So light can reflect, it can refract, it can interfere, it can diffract, it disperses, it can be polarized. These are all wave properties, and every property light displays them, right? So in the late 1800s, especially then with Maxwell's theory work of being able to show that a change in electric field up and down creates a magnetic field that is at right angles to it, and that's what an electromagnetic wave is, that it just seems certain that, light is just got these wave properties, right? You can go right down the property list in a SCOTUM, and theory tells us that, light behaves this way. And so, in the late 1800s, optics is sort of this well put together package. Electricity and magnetism with Maxwell and his work is kind of well put together. And then you got mechanics, the laws of from Newton. Newton's laws of motion, that's well put together. And so whether it's true or not, people like Lord Kelvin, and he's a chemist, so he's probably a lunkhead, so it's probably true, was telling the students, don't go into like physics because it's all done, right? You got Newton's laws of motion, you've got optics kind of really worked out, electricity and magnetism are worked out, and there's not a lot to do that's left. And so that's the nature of physics around 1890 or something like that. And typically there's always a few threads to kind of clean up and so forth, but once in a while when you pull on those threads, right, the floodgates open up, and that's what's going to end up happening here. You know, the next chapter, what we'll be looking at though, is using these properties here and just seeing how people make simple technology, right? Simple reading glasses out of refraction, and maybe how we make mirrors out of reflection, and you know how we maybe make a telescope and these types of things. So we'll take a look at some different optical instruments here and how people use those. And then we'll start looking at, you know, somebody's going to show up and start pulling on one of those threads, and that'll be Albert Einstein. And then he will, you know, really open up the floodgates to, oh, you know, we didn't really know as much as we kind of thought we did. So that's where we are at in the course, and that's where we are going. So hopefully this kind of helps you with some of the stuff in chapter 24. And I'll see you soon. I'm going to go eat lunch.